Hello, class. Today we're going to be talking about vectors in lesson 9.4. And vectors are something that are usually studied in a physics class. And so those of you who have taken or are currently in physics may have studied some vectors already and may know a little bit about vectors. And so there are many applications that we can use vectors for, both in math class and in a physics class. And so what vectors are they are directed line segments. And so you might remember line segments from, say, like a geometry class. A line segment has a starting point and an ending point, whereas a vector has a starting point and then it's directed in some direction. And we say that what makes a vector unique is the direction that it's pointing in and the length of the vector. And we're going to use the word magnitude to refer to the length of the vector. And so, as I mentioned, vectors have very many applications, especially like in a physics class. It might help us solve problems dealing with velocity or displacement or acceleration or any type of problem that involves movement. For example, we might do a problem that involves an airplane or an aircraft of some sort. So again, the direction of the vector would tell us which direction the aircraft is traveling, and then the magnitude actually tells us information about how fast it's traveling. So you might think that it has to do with how far it's traveled, but as we'll see eventually, that it would indicate the speed or velocity of the aircraft. So one thing that's kind of unique about vectors is that we consider all vectors with the same direction and the same magnitude to be considered equal. And so we might look at all these and say, well, these are different lines. They may have the same slopes, but they start in different places. They have different y-intercepts. Whereas that might be true for lines, for vectors, these are all considered the same because the two distinguishing parts of a vector are the direction and the length. And so if the direction is pointing the same and the length is the same, then we consider all of these vectors to be the same. So each one of these vectors would be considered equal, and I can make more of these if I wanted to. I could copy and paste and make an infinite number of vectors. As long as they're pointing the same direction and they have the same length, then they are considered to be equal. One of the many things that we can do with vectors is add them. And we will see that we can add them algebraically, and then we can also add them graphically. And what I want to do right now is first focus on just the graphical representation of what adding a vector might look like. And so as we start this, just keep in mind direction is very important. And so if I were going to do something like, let's say, a plus b, what that means is you pick a starting point, and the starting point does not matter. It could be, if we were using a coordinate plane, it could be the origin, it could be any other place, just like if we look at this picture, see how the starting point is different places for each one of these vectors. And so the starting point really isn't important as far as finding the sum. And so what we do is, if we're starting with A, we're going to head off in the direction of A and in the same length of A. And so I'm going to start at the point that I designated and then head off in the direction of A. And then when I add B, what I do is we kind of start where A leaves off. And so if I were to call this maybe like the tail of A and the head of A, and so the head of A becomes the tail of B, so to speak. Whoops. And so wherever we left off with A, that's where you start with B. Okay, so again, the head of A becomes the tail of B, and so we head off in the direction of B, that distance that B is. And then wherever you land let's say right here, um, the new vector that you would create by starting at your original point and going towards that landing point, that's going to be your a plus b. And so we can't really see the arrow here, I'll just add one here. Because remember, direction is important. So what a plus b is it's kind of as if you had traveled directly to your ending point. So like if this is your starting point and you go in the direction of a and in the distance a, and then you land here, and then you head in the direction of b for that distance of b, and then you land here. And so what a plus b is it represents the vector that would have taken us straight to this point from your starting point. So instead of going like kind of up and then down a little, it's just straight over, up and over. And so that's what a plus b represents. One of the cool thing about vectors is that addition for vectors is commutative, just like adding real numbers is commutative. And so what that means is, let's say I wanted to find b plus a. The commutative property tells me that a plus b and b plus a should be the same if I were dealing with numbers. And so it's actually works, it's a property that works with adding vectors graphically as well. And so we can see that play out here. Let's say, again, just pick a starting point. And let's start with b this time. So we're going to start with b and then go in the direction of a. So let's, here, let me copy b just to make sure it's a perfect clone, if you will. And so I head in the direction of b from that starting point, and then I'm going to add a. So from the ending point of b, we're going to go in the direction of a. And then the new vector b plus a will be represented by starting at the starting point and heading the direction towards where adding a left off. Okay, so here was our original point. And so we could call this b. And then we added a. And so the vector that starts where our original point was and ends where when we added a left off. So if we were just to go directly to that point, that would be the vector b plus a. Now you might be wondering, well, how does that prove the commutative property works? Well, check this out. This is kind of neat. So let's take this b that we used, and let's go back to this picture. So our original starting point was right here. So if I were to have gone in the direction of b, and then from that ending point gone in the direction of a, do you see how I ultimately end up in the same place? So it doesn't matter if I go, kind of up and to the right and then down, or if I go down first and then up and to the right. As long as I'm going the same direction and the same distance for each of them, then ultimately my landing point will be the same place, which is a plus b. So this is just showing that the a plus b, the original a plus b, which was this vector here right in the middle, ends up being the same as b plus a, which is also that vector in the middle. So just to kind of confirm that, vector addition is commutative. So if I have a vector v and add w, that should give you the same graph, same picture as w plus v. Also, a little bit later, we'll start to express our vectors algebraically. And so not only does it work graphically, but it works algebraically, that you can commute those two vectors and get the same result. Vector addition also happens to be associative. You might remember associative is when you're adding three numbers and you just change the order of operations by changing your parentheses. So you could add v plus w and then add a third vector u, or if you wanted to, you could add u plus v and then a third vector w, and doing both orders of operations would take you to the same place on the graph, or algebraically it would give you the same result. Subtracting vectors is pretty similar to adding vectors. So in the same way, it doesn't matter where you pick your starting point. And so let's say I was wanting to show a graphical representation of A minus B. So what I would do is I would pick my starting point and go in the direction and the distance of A. So that would take me here. And then normally, if let's say I were adding B, so if I were adding B, since B is pointing down, I would take this vector, let me make a clone, and pick up where I left off at the end of A. And so I would head in this direction, and then my A plus B would be down here. Well, in this case, I'm subtracting B, so you can maybe pause and think about what that might look like. And typically, when we subtract, that means go the opposite direction. So what I'm going to do is instead of going down and to the right, I'm going to go up and to the left. So I'm going to go this way, and I'm going to point my arrow around. And so I'm going to make this kind of like my ending and new starting point, and then my arrow is now pointing this direction. And so then A minus B will be the vector that's represented by what if I had started in the same starting point and then ended, went directly to my new ending point. And so that would be this vector here. And let me show the direction just to be clear about that. When you draw these in your homework, it's really important that you show your starting point and then put an arrow so that we know which direction you're going. Because if the arrow is on the other end, that's a different vector. And so it's really, really important that not only do we show the length, I think that part will come naturally and obvious, but it's very important that when you draw these to put your arrows to show the direction as well. And so this would be A minus B. So this would be A, this would be negative B. Okay, and that would be the same as like if I said A plus negative B, right? So again, A plus B would take me down this direction, but if I'm adding negative B or subtracting B, I would be going the opposite direction, and so the new vector ends up over on this side. It's also important to point out that vectors with the same magnitude, so the same distance, but they go in opposite directions, those will always be 0. So we could represent that by saying V for vector plus negative V would just be 0. And that's going to be true algebraically, but that's also going to be true graphically. Okay, for example, if I started here and went in this direction, and then from that point, my new ending point, if I just went in the direction of negative V, that would just take me right back to where I started. And so if you think in terms of velocity or displacement, it's as if I didn't do anything. The object is still right where it started, and so we could represent that with the number 0. We can also multiply vectors by what we call scalars. Scalars are kind of like the coefficient in front of a number of a variable. And so like if I were to say like 5x, 5 times x, so 5 would be like a scalar in this case. And so let's say I have the original vector v that is this distance and goes in this direction. Well, if I were to multiply v by 2, I would get 2v algebraically. And so all that would mean is I'm going in the same direction, it's just I double the length. And so if you were just to make 2 copies of this, you would end twice as far away. If I did a half of v, that would just take half of the length. And so the direction is still the same. We just go half of the distance. And if I were to have negative v, the coefficient would be -1. And so that means since the absolute value of -1 is the same as 1, the distance would be the same. But since it's negative, that would just take me in the opposite direction, kind of like subtracting does, like that we saw on the previous slide. So one of the things you're going to do in your homework, I'm going to run you through a few examples, is they're going to ask you to graph given some vectors. And so I have 3 vectors here. Each have different directions and lengths or magnitudes. And so this first example wants us to do v plus w. So again, when you're sketching these, you don't really need graph paper. I suppose you could use graph paper and start at the origin if you wanted to. We're actually going to talk about that here in a few minutes. That's a vector that has a special name, but you don't have to. So you can just draw a sketch without graph paper. So just pick a starting point. Make sure you give yourself some open space. And so if I were going to start with v and then add w, what I would do is first go in the direction and the magnitude of v. So I'll do that. And when you're drawing these, if you can show your direction, so make sure your arrows are visible so that we know exactly which direction you took to get to where you're going. And then if you add w, we'll just pick up where v left off. So if v stops right here, where my blue arrow is, and then I head the direction of w, I ultimately land right here. And so this is v, this is w, and so the new vector v plus w would be the vector that we would have created by starting at the same starting point and heading towards the ending point that you got after you traveled w. And so make sure again you put your arrow. Actually, I guess I have 3 arrows here, right? I went this direction and then this direction to get to w, and then ultimately v plus w is headed this direction. So I'm going to write that down here, v plus w, that's my new vector. All right, here's another one. This one wants us to show u minus v. So again, just pick a starting point, and then we're going to start with u. So from that starting point, oops, I cloned the wrong thing. Let's try that one more time. Oh, there we go. All right, so we're going to head in the direction and the magnitude of u. So that lands us right here. And then we're going to subtract v. So if I were adding v, I would just pick up where I left off and head in the direction of v. But since I'm subtracting v, that means we want to go in the opposite direction. Instead of pointing to the upper right, we're going to point to the lower left. And so I want my arrow to show that as well. And so that's going to take us this direction. And then our u minus v again is start back at your original starting point and then head towards where we ended. So if this was u and this was minus v, this vector over here would be u minus v. So starting here and heading in this direction. And then here's one last one. I wanted to show you that you can have vectors where you use more than 2 vectors. And here's also one that shows a scalar, so it'd be interesting to see what that looks like. So I'm going to try to give myself plenty of space here. So I'm going to start with start with just, again, any starting point, so 2 u's. So let's start with 1 u from our starting point. And there we are. And so then wherever that lands, you're just going to go that same direction another u. And then we're going to add w. And so notice w is pointing down, so I'll just head whatever direction w tells me. So I kind of have like a u here, I've got a u here, and then I have a w. Okay, this part is represented by 2u. And then we're going to subtract v. So we've got one more. If I were adding v, I would head this direction, but since I'm subtracting v, again, we go the opposite direction. And then your final answer, and I probably should have put my arrows here all along just to kind of show the route I took to get to where I'm going. And so my final answer is the vector, again, starting at your original point, heading towards where you ultimately ended. And so I'm going to show the direction there. And then it's not a bad idea to label this. So this would be 2u plus w minus v. Here's minus v over here. All right, so that's how you graph vectors. So I have some more definitions and things, just some other ideas I want to share with you. Again, today's really just an introduction to vectors. So, we looked at the graphical side of things, a little bit of algebra we're going to delve into here. And again, just a very, very brief introduction so that later we can actually start to do some things. And so we're going to call any vector where the magnitude is 1, we're going to call that a unit vector. Okay, and so you might kind of think of way back in middle school, we had these things called unit rates. That was when we had a rate that compared to one, so like 50 miles per 1 hour would be a unit rate, or $3 uh, per pound would be a unit rate per 1 pound. And so when we think of unit rate, or in this case unit vector, it's referring to the unit of one. And so um, to help us talk about vectors algebraically, or to help us graph them on a coordinate plane if we wanted to, we are going to use the letters I and J to help us out. So where normally we would have the x-axis, we're going to use I along the x-axis, and I is going to be the unit vector whose direction is along the positive x-axis. And so you can see I have down here in blue here, this vector I is starting at the origin, and it's heading towards the point 1, 0 and stops there. And then J is going to be the unit vector whose direction is along the positive y-axis. So it will also start at the origin and head up to the point 0, 1. And so if I wanted to just quickly sketch a graph, what does the vector 2i plus 4j look like? And so this is how we're going to show vectors algebraically often, is using I and j. And so if I is along the positive x-axis and j is along the positive y-axis, if I wanted to graph this vector, I would just go over 2 units to the right and then up 4 units. And then that would be my point where my vectors land. And so then the vector 2i plus 4j would be represented by the vector that starts at the origin and heads to the coordinate 2, 4, or what would have been 2, 4 had this been the xy coordinate. Instead, we call this 2i plus 4j. Another definition with regard to vectors is something called a position vector. And so you might remember earlier we had talked about how vectors, it doesn't matter where they start, as long as they have the same direction and the same magnitude, we consider them to be equal. And so what a position vector is just a specific vector that starts at the origin. And so it can be really useful to use position vectors just to give us reference. And if we're starting at the origin, that's often a good place to show reference. And so one of the things they're going to ask you to do in your homework is they're going to give you 2 points, P and Q. And it's really important. You'll notice that they're saying P is the initial point and Q is the terminal point. And that's going to be, that's going to be really important to us as we try to answer this question. And what they want us to do is they want us to write a vector in the form AI plus BJ that is its position vector. So first, let me show you, maybe we could just graph these 2 coordinates as if this were like a XY coordinate plane. And so if I were to graph these coordinates over 3 up 2 and over 5 up 6, so this would be my starting point. So if I wanted to make a vector out of this, I would head towards the direction. Notice it said the terminal point is Q. So if I head towards the direction of Q, so starting at P here and heading towards Q, this would be the vector that we found. And so all they want us to do is find the vector that's equal to this one but starts at the origin. And so essentially what we're doing is we're picking this vector up and it's like we're translating it or sliding it down to the origin. And so if I were to do that, my new coordinates would be 0, 0, and 2, 4. And so 2, 4, if I wanted to write it in the ij form, I would say over 2, so 2i plus 4j. Now, there's 2 ways you can do this. You can use graph paper and to like physically translate it, so move it over. So you could kind of tell yourself, well, if I wanted to move this point to the origin, I'd have to go left 3 and down 2. So you could like physically do that, and as long as you follow the same direction or rules for this coordinate, you'll get to 2, 4, right? If you go, if you had to take the 3 over 3, that means that we're going to have to take the 5 over 3, and that lands you at 2. And then for the 6, I had to take it down 2 units. And so if I'm taking it down 2 units, or sorry, if I take the 3, 2 and take it down 2 units, that means I have to take the 6 also down 2 units. And so if I start at 6 and go down 2, that's going to take me to 4. And so that's where the 4 came from. Now, it's probably way easier just to do this algebraically rather than graphing it by hand and kind of counting out what the displacement is. So we can do that very easily by just matching up the y values and the x values, or the j values and the I values. And so if I want to know when I picked this up and moved it down, what is the difference? All I have to do is subtract. I can do 6 minus 2 gives me 4, and that's going to be my I value. Sorry, that's going to be my j value. Let me actually take that back. Let's do the horizontal change first. So let's do 5 minus 3, and that's going to be my I value, since the 5 and the 3 are my x coordinates. And then so that's going to give me 2i. And then I'll do the same thing, 6 minus 2 for the j. And so 6 minus 2 gives me 4j. And so when you look at this, you might say, well, this looks kind of reminds me a lot of my slope formula, y minus y over x minus x. The only main difference is that whereas with the slope formula, you can subtract to either direction, like I could do 6 minus 2, or I could do 2 minus 6. We actually don't want to do that for this formula. You always want to take the point from the terminal side and subtract from the initial point. And it's really important that we do that. So again, always start with the terminal point, subtract the initial point. And the reason why is that will give you the correct direction. So for example, if I had gone 2 minus 6, I would have got -4, and 3 minus 5 would give me -2. So that would end up going left 2 and down 4, and my vector would be headed in the opposite direction. And so for these two vectors to be equal, we have to make sure they're going in the same direction. So to ensure that they're going in the same direction, you want to take the coordinates of the terminal point and take away the coordinates of the initial point. And that is the quickest and probably the best way to come up with your new position vector. And so here's one we can maybe do real quickly without graphing. And so same thing, P is my initial point, Q is my terminal point. And so if I wanted to find the I value, start with the terminal point first. So Q value for X is 6, and I'm going to subtract -2. And that's going to be my I value. And then I'll do the same thing for my J value. I'm going to start with the terminal Y value or J value, -2, and I'm going to subtract -1. So then now it's just a little bit of math. 6 plus 2 is going to give me 8i. And then here we have -2 plus 1, so it's going to be -1j or -j. Okay, so when you do these in your homework, this is certainly the fastest way to do it. You don't have to graph them. You certainly can graph them, and you could, physically translate the vector over to the origin and see how much it changes. But you don't have to. The easiest way is just to do it this way, and just to kind of remind you one more time that when you're doing this, it's just simple subtraction, but just make sure you do the coordinates from the terminal point first, so the 6 and the -2, and then subtract the coordinates from the initial point. That way you can ensure that your vector is headed in the right direction. All right, just one last thing. This is, again, just another kind of a quick definition or formula. We talked about the magnitude. Again, the magnitude is just the distance of the vector. And so one way we can denote magnitude is they use these vertical bars. So anytime you see these vertical bars, it's kind of like absolute value, but there's 2 bars. And so it's just the notation our book uses to show the value of the magnitude. And so when you see those bars, that's what they're asking you to do. And to find the value of the magnitude, since it's a distance, and it can be the distance of a right triangle, we can simply just use the Pythagorean theorem. And so if, let's say V is the sum of vectors A and B, the magnitude of V should just be the distance of that hypotenuse. And so because of that, the formula just reads, it'll be the square root of A squared plus B squared. And so to see how that plays out, let's say, again, we're going to use that I and J notation to write our vectors algebraically. And so if I wanted to find the magnitude, it's simply just plugging these values into the Pythagorean theorem. So it'd be like -2 squared plus -4 squared. And a little bit of math. This will be 4 plus 16. And so that will be root 20, which is better written as 2 root 5. So again, just to visually kind of show how that plays out, if I were to go -2i, that would be going to the left 2 and then down 4. And so my new vector would land right here, and so vector v would be headed this direction and this distance, and that's what we're trying to find, is that distance. And so if this is -4 and this is -2, then this distance here should be 2 root 5, the hypotenuse of that right triangle that we created. Okay, so I think the last couple problems in your homework ask you to find magnitude given a vector in this algebraic I and J form that we're going to use. And so it's just as simple as doing the Pythagorean theorem. All right, well, that kind of wraps things up. Sorry again for a longer video. We had a lot of things to discuss since vectors are pretty new to us. And so I think your homework really shouldn't be that difficult. I think you'll find it pretty easy once you kind of get the hang of drawing vectors. So you'll find it on page 621, starting with number 11 through 28. I'd like you to do all of those. I believe the first section is multiple choice, and so they give you some vectors and some graphs. And I take that back. I was just double checking. Actually, the first several you're just going to graph by hand, kind of like we did those first 3 examples. And then the second section is what I was thinking of. It's actually not multiple choice, but it's true false. And so what they do is they give you some pictures of vectors and some sums and differences of vectors and ask you whether those results are true or not. And so, and then you'll have some problems where you find the position vector. And remember, the position vector is just the vector that starts at the origin. And so that was like 2 examples ago. And then the last couple problems, they'll have you find the magnitude using the Pythagorean theorem. So the math is not hard at all. It's just adding, subtracting, and Pythagorean theorem if you can do that. But the graphing, take a little bit of time on and make sure that you understand that well, how to show the sum and difference of vectors graphically. All right, good luck with this. We're going to have another lesson on vectors on Friday, kind of a day 2. If you have any questions on this, you know how to find me.